So in this next one, we're going to talk about the continuous compound formula, or continuous compounding events. In one of the other videos, I talked about exponential growth and decay models, right? And in these videos, we utilize these this formula, A equals the principal amount times 1 plus or minus r taken to the power of time. When it is continuously occurring, or continuously growing or decaying, we use a different formula. We use this other formula called the continuous compound formula, which is the IPERT formula, or also referred to as A equals P times E to the RT. There are many different types. A lot of people may see it like this if they take a college algebra class. We're going to focus on this one, and we're going to focus on the applications of compounding appreciation. So first off, we got to notice that our base of the exponential function, or the exponential base, is actually an irrational number. If we remember back to prior math classes, we remember that E is approximately equal to 2.71818. And that pattern goes on forever and then ends with a 2.8. It is Euler's number. It is an irrational number, and as such, we're utilizing this, what we call the rate of natural growth, or the natural growth of exponential growth, as the base of a continuously compounding event, meaning every time it happens, it's going to compound on top of itself and grow even more. Okay, so P is often referred to as the principal amount. Okay, P is the principal amount, once again, which is the original amount you have. Principal amounts, principal invested, investment, or amount of material. Okay, so it's principal amount or investment. Principal amount of material, like X number of bacterial cells or whatever, right? So we're going to focus on this formula given the fact that bacteria grows continuously. Okay, so let's say you have 4 cells, 4 bacterial cells, so 4 cells of bacteria. Over time, the constant rate for this bacteria is 0.3, and we'll say percent. Okay, how many cells after T equals, let's say, 5 days? Okay, and let's change that 0.3% to just 3%. Okay, we're going to do that. Okay, so the original amount, the amount I'm going to get afterwards, is A equals P times E to the R times time. Okay, the original amount I had, or the principal amount, was 4 cells of bacteria times E. The constant growth rate was said to be 0.3, so 0.03, which is 3%, times 5 days. Okay, well, this is approximately how much? You plug it in your calculator, whatever calculator you have, it doesn't matter, and make sure that you have these two things being multiplied together and put them in parentheses and in the power position. So after 5 days, I have 4.6473369771. Now that's not really a good example, mainly due to the fact that we know bacteria grows fast, right? It grows really fast. Some bacteria grows really slow, some bacteria grows fast, some bacteria has a medium growth rate. But basically after 5 days, I have 4.64 cells. So I almost have 5 cells of bacteria. If we had changed that to 30%, right here, if we change that issue to 30%, then basically what I'm going to do is I'm going to plug in 30. Okay, so I'm going to plug in 0.3. So I know that over time it's going to grow with respect to 0.3. That, of course, will change the whole outlook and answer. If we change that to 0.3, then we're going to get the following. Plug it back into your calculator. 4 times E taken to the power of 0.3 times 5. Well, if it grows at a constant rate of 30%, then after 5 days we'll have 17 cells, 17.926 cells. Well, let's go at 8. 17.9268 cells of bacteria. So the greater this number right here is, the faster it grows. This just acts as a multiplying effect, so that each day it grows by a certain rate. In this case, it grows by 30% each day of whatever E is. And then you multiply that by 4. So the principal amount, the more you have up front, and the faster your growth rate, the faster the overall growth of continuous compounding event will occur. So this is an example of where you would have continuous growth over time with respect to 4 cells of bacteria. Another aspect is finance. Suppose you put an initial investment. Let's say you place $4,000 or $44,514 into an account that has a compounding rate continuously of let's say 0.3%, mainly because banks, the lower the amount of investment, they're not going to give you a really good compounding rate. Let's see, what would be the value of the initial investment after 6 years? Okay, so after 6 years, you leave it into account. Remember that the interest accrued, or the amount accrued, is equal to the principal times the base E taken to the power of R times T. Okay, so the principal amount is $4,514 times E to the power of 0.0, and it's 0.3%, so it's not even 0.01, it's 0.03 times 6. Okay, we plug that into our calculator, so 4,514 times e to the power of 0.003 times 6. So after 6 years, you get $4,595.99. It's not really a good rate, is it? So that's not really that great, but it does grow. Depends on the growth rate, and when you go to banks, you got to watch out for the rates that they're trying to offer you. Well, let's change that value to, let's say you now find a better company that now gives it at 13%. Let's say you've got a phenomenal rate and they're going to give it you for 13%. Well, highly unlikely, but let's just say you get 13%. Change this value right in here that I'm erasing, and now you're going to plug in 0.13. This is going to change the value of it significantly. So you do 4,514, which is the principal amount, times e to the power of 0.13 times 6. The investment after 6 years will be worth $9,847.17. So overall, you gained a whole lot of money because you had a better rate. Also, another thing that can affect your growth is the principal amount you put. The more upfront you can put into the investment, the more you can grow. So those are two multiplier effects that come into play when talking about compounding continuously, specifically for bank rates or bacterial growth or whatever. Another aspect of this is half-life, which is talking about radioactive decay. But we're just going to focus on compounding continuous and on growth models at this point. So I hope you've enjoyed the video. Please, if you have any comments or questions, feel free to post them at the bottom of the video.